The first of these equations that we're going to look at as we apply to a control volume is the idea of conservation of mass. Remember from physics, matter can't be created or destroyed. It's a pretty simple concept, so whatever mass flowing in has to equal what mass is flowing out. So first of all, remember we're going to be dealing all of this with a control volume because we need to look at what's coming in, what's going out. So if you look at A, what's coming in here has to equal what's coming out there. Unless we relate the laws of physics and throw a black hole in the middle of that, that's what's going to happen. So let's talk about mathematically what is going on. So conservation of mass tells us that the change in mass with respect to time across the system has to equal 0. So if we look at that, that tells us that the mass of the system, as we integrate the mass over the system, dm has to equal the integration over the volume of the system, density dv. Because remember, if we integrate the density over the volume, it's the same thing as saying rho v, and that'll give us the mass. Now, what ends up happening is when we put this through Reynolds transport theorem, we end up with an equation. And as I said, all the Reynolds transport theory equations have the same form to them, and they're really talking about how the intensive and extensive properties relate to each other. And so in this case, we're looking at the change in mass over the time of the system, as we said, has to be equal to 0. And so how do we track that out? Well, we need two parts. First, we need to know, is the mass changing inside the control volume? Once I draw that boundary, what changes in the system? So what we do is we look as a derivative of time, we integrate over the control volume, and we look at the density over the control volume. So that entire term is how is the matter changing within the control volume? I just want to point out at this point for those of you that are checking out because you're like, oh, that's way too much math. Don't worry, we're going to make some simplifications, but I want you to know where we're starting from. So that is what's going on in the control volume. So in the control volume. Well, now what we need to do is we need to add to that what's coming in and out of the control volume through the boundary. And so the way that we do that is we look at the density, and then we're going to multiply that by the relative velocity vector dot n. So n is the normal. I'll talk about that here in a minute, refresh you from your calc classes. But we're going to integrate that over the control surface. And so this is what's moving through the boundary. And so we have to, all that has to be 0. Whatever changes in the control system has to be balanced out by what's coming into and out of the system. Now, this is a pretty, not complex, but a pretty long equation. So what we have to do now is we have to start making assumptions. And assumptions are very, very important in fluid mechanics because there's a lot of weird things going on. And so sometimes you make assumptions, sometimes you don't. And so it's really important not only to know which assumptions you're making, but why. Now, I will let you know on the exams, you'll be required to put the assumptions down. And I sometimes will ask you why you made this assumption or that assumption. So it's not important just to throw down all the assumptions that you could possibly have because that kind of stuff will get marked wrong. I would like you to at least have a general understanding of what assumptions that you're using. So now let's start looking at those assumptions, and I'm going to start tallying them over here. So typically when I do a problem, and we'll just write assume over in the corner, and I'll start tabulating my assumptions. First assumption that we're going to make is that we're using a fixed control volume. So fixed control volume means that it's not deforming. So that really should mean the density is not changing with respect to the volume. And so what ends up happening is our little equation here, that's not a partial derivative, it's a total. So the mass of the system is still equal to 0. We're able to clean up that first term a little bit and just say that's the integration of control volume Now we've got the partial derivative of the density with respect to time over the volume. And then we still have all this stuff over here with the control surface. Rho VR dot N dA. So it makes it a little bit simpler. That cleans things up a little bit. The second thing that we're going to talk about is one-dimensional inlets, outlets. So what do I mean by a one-dimensional inlet and outlet? So it's really a mathematical thing, because we're dealing with this dot product right here. VR dot N. And so what is that? Well, that is the velocity vector dot product with the normal vector of the surface. So if I look at my control surface here, and I have my velocity coming out at this place, and then I have the orthogonal, or the normal vector to the surface that's coming out there. And so I'm going to have some angle between them, alpha. So what happens is, if we go back to math, our v vector dotted with our normal vector, to do that calculation, we'd have Vn times cosine of alpha. The problem we get into there is actually just having to calculate out that alpha all the time, because our normal vector is going to end up being 1, because normals are 1. So what we do is we redraw, or we just draw normally, our control volume, so that the velocity is coming out, or coming in, normal to the surface. Kind of like when we were talking about control volumes, and my velocity, I drew my control volume in such a way that the velocity vector came out of the control volume normally. So what ends up happening is we can get rid of this if we rotate this and draw it. So then, okay, well now my v dot n, I have either the cosine of 0, or if it's coming in, I have the cosine of negative 1. Or sorry, cosine of 180, which would be negative 1. So cosine of 0 would be 1. Cosine of 180 would be negative 1. So basically anything that was exiting, so if we had a normal exit, what ends up happening is that v dot normal, the v dot the normal would end up being what? Well, it's just going to be plus v. And then, so that's a normal outlet. So if I have a normal inlet, and I'm not talking about normal as in regular, I'm talking about normal as in 90 degrees from the control surface. So my normal inlet would end up being negative v. So what that allows us to do, we make that inlet and one-dimensional inlet and outlet assumption. I mean, we still have the change of mass over the system, still going to equal to 0. We still have this partial density with respect to time, dv. That's everything inside the control volume. So now what we end up with is we have this case where, okay, so I know that v dot n, since it's all going to be normal, the stuff that's coming in is going to be positive v, stuff that's coming, is going to be negative v, the stuff that's coming out is going to be positive v. And so now I take that v, I multiply it by my density, well, and then I'm doing dA, so the integration of the control surface. So at this point, basically what I'm doing is I'm just going to be adding up everything coming in and everything going out. And when I do the integration of the control surface of dA, that's just going to give me the area of that input and output. So that entire, with that, as long as we draw our control volumes to be one-dimensional inlets and outlets, this entire integration part here at the second just becomes a couple of summations. So we're going to sum, and we're just going to sum up I, how many ever there are, of rho, A, whatever that inlet or outlet is, V, whatever is going on at that point. So it's all this stuff coming out, because that's our positive, because of this guy right here, our normal outlets, minus, and I'm going to make a little room here, get rid of my thing, so minus the sum of rho, A, V, once again, I number outlets of what's coming in. And so now it's pretty easy because it's just, okay, what's the density, what's the area, what's the velocity coming out, subtract everything that's coming in, and that gives us our change in matter that's coming through the control volume. So we have one more assumption that we will make, and this is probably a fluid mechanicist's favorite assumption, is what we call steady flow. What does steady flow mean? Steady flow means it does not change with time. I can sit there, and if I turn on a hose and it's coming out at 1 foot a second, and I leave it there, and I come back 5 minutes later, and it's still coming out at 1 foot a second, I come back an hour later, it's still 1 foot a second, it's not changing. It's a steady flow. It's steady with respect to time. Now, the interesting thing about that steady flow assumption is what that does is anything that has to do with time, any derivatives that have to do with time are going to become zero. Because, since it doesn't change with time, there is no differential with respect to time. So if I do that, that takes this entire term, because of assumption 3, and it will drop out. And so what you're going to be left with is the change in mass of the system. It's going to be 0, and we're just left with that sum of rho AV out minus rho AV in. Now this is the basic formulation of conservation of mass when you make those 3 assumptions. If you don't make those 3 assumptions, you have to go back and solve the original equation that we started out with.